Today's session is going to be on bundle D of 124. This is mostly on the concept of how processes are given time on the CPU, the ideas and algorithms on how we can say this process gets this time on CPU, this process gets this much time. This is the order we do it. Last time we sort of vaguely hand waved this way. This is when we'll go detail. So the idea is if we have, for example, 3 processes, I'm not sure. We have 3 processes, and we're trying to figure out how do we have, which order do we put these on the CPU? How long do they get on the CPU? If we're going to have a time, a set amount of time that something can have, and that is an important distinction to make. You either have preemptive or non-preemptive. So that is huge. There we go. So preemptive means that you are interrupting before completion. Or you have the possibility of interruption before completion. So as I'm going through, some of these algorithms will be preemptive, some will be non-preemptive. The simpler ones will be non-preemptive. They'll just take a process, put it on the CPU, and leave it there until it either waits or terminates. Whereas preemptive ones will interrupt them and say, no, you've had your time for someone else to go on. There are various types of things we want to be dealing with when it comes to this, like the criteria we want to be looking at, and say, okay, what is this algorithm trying to achieve? And these are examples of what we're trying to do. That's all the things that we want to in the best case scenario. We want all of these to be true. That we're maximizing the number of processes being completed in some given amount of time, reducing the amount of time a process is being left unworked, and minimizing the amount of time it takes for a process to be completed, minimize the time a process is waiting, maximizing the amount of efficiency of the CPU. We want to make sure it's not sitting around doing nothing for as little as possible. And also we want to be fair. We don't want one process getting all the time on CPU, whereas another is getting no time at all, because that's starving that process. And it's very rare we actually want to do that. So most of those will be. It's one of the cases where you can't get all of them. You're never going to get all of them. It's pick which ones you want most, and then aim at those. And different algorithms will aim at different ones. The first of these algorithms, the very simplest, is first come, first serve. Is it this color? Let's find out. Yes. Okay, so this algorithm is basically a queue. So if you think of the data structure of a queue, it follows the principle of first in, first out. FIFO. Processes are completed in the order that they are given, in the order that they appear. So actually, the oldest processes are completed before the youngest processes. It is non-preemptive, so it will not interrupt a process before it's either waited or terminated. So a process has complete control of when it relinquishes control of the CPU. Image. Where's the image? There's the image. Push. There we go. So, if we have these 3 processes, P1, 2, and 3, and we know that this technology burst of 13 milliseconds, that means it will take 13 milliseconds for it to complete. Using first come, first serve, we will put them in just in the order that we got them. So 1 first, then 2, then 3. And so you'll see that this is what it will show up as. This type of chart is called a Gantt chart. P1 goes first, it takes 13 seconds. P2 goes second, it then takes 18 seconds in total because it has a 5-second length, and then a 1 second for 3, taking it to 19. If we wanted to find the average time that a process is waiting, then we will have to find the average of adding up all of their wait times. So P1, that doesn't wait at all. That's just 0. P2, that has to wait 13 seconds because it starts at 13. And P3 starts at 18. So it has a waiting time of 18 seconds, or milliseconds, sorry. And then all of that over 3 will give us our average time. I don't have a calculator. How is it the only time I don't have a calculator on my desk? One moment. 0 plus 13 plus 18 divided by 3 is 10 and a third. So the average wait time for this is 10 and a third. And you can see that, well, this isn't the best way of doing it if we're trying to minimize average wait time. This is not optimal. It's very simple to implement. It's just put all the processes in a queue, serve them one by one. But it's not optimal. It's not going to be regular, because if the order of processes is in a different order, then the wait time is going to change as well, the average wait time. If P1 was last, then you would get a very different rate. If you reverse this order, then it would be 0 first, then 1, because P2 will go to second, and you have 5 seconds, then plus 6, and then all that divided by 3 is a much smaller number than what was there. So your efficiency will change drastically just on random chance of when processes are created. Also, point note, this burst of 13 milliseconds, we're given this is the burst. In reality, you'd have to be estimating these. You can't reliably say this is how long a program will take to run. That's the halting problem. It's impossible to do. Oh, impossible to do for all programs. Some of them can be done. So it's not feasible to just say this is how long this program is. We can estimate though using how long previous ones have done and all the rest. The other issue is that because this is non-preemptive, it can't be used in time-sharing systems such as your average desktop PC. It's just not going to work. Time sharing is required for those systems. You have to interrupt at a regular interval to have the illusion of simultaneous execution, so that users aren't waiting however long it's going to take to get a response. Okay. Next bit is shortest job first. I think.
So shortest job first is essentially just a non-preemptive, like first come first serve type thing. So if we look at it, so it's non-preemptive. That's huge. Second. So it's a non-preemptive. Essentially, like it can be interrupted on the CPU if it has not finished doing what it's doing. So say the CPU hands out times of 5 seconds and you get a job that's 10 seconds in the queue, it'll be interrupted after 5 seconds and then sent back to the back of the queue in order for it to...
That's the next one, Elliot.
Oh, is it the next one?
Yeah, this is the non-preemptive means that it is
non-preemptive.
Oh,
I'm reading this wrong. Non-preemptive. So again, don't mind me then. It works in the same way, so it just gives it the amount of time that it needs. And it maintains a priority, so it's a priority queue, based on essentially the shortest job. So rather than taking things in as they arrive, it maintains its sorted order, and that's going to be using the estimated burst time. So sorts queue. And because it's going to sort on that, we know that essentially the jobs that are smallest will be at the front, and then the ones that are large will be at the back. This could create some issues. Say you get lots of jobs that are really small, and then you have this one job at the back that's really big. It could take a long time for that job to get done. so it could starve some larger programs of getting the CPU time. But given all the information it needs, so given perfect information, this can be optimal. As it can successfully get rid of all the shorter jobs and then quickly get onto the longer jobs before new shorter jobs are assigned. And that, again, that's only given perfect information. That will only be if you get like the exact amount of time needed for each job on the CPU, not just rough estimations. You need it down to like the milliseconds, probably even shorter than that. So yeah, essentially just make sure there's some kind of order to the queue, and then we can go on to the next one, which is quite similar. And I can go back to talking about preemptive, which is shortest remaining time first. If I can figure out what color that is, I think it's this. So shortest remaining time first is essentially a preemptive version. What the hell happened there? Preemptive version of shortest job first, meaning that queue is still maintained. What is going on? I tell you what it is. You stop charging. So the queue is still maintained throughout this with the shortest job first, and so if it's preemptive, it's going to interrupt at certain intervals. So let's say it interrupts at 5 seconds. So you've got a couple jobs in the queue. So say at the queue you've got one that's 3 seconds, one that's 5, and then one that's 10, and the CPU allocates 5 seconds. Then you're going to see that this third one will get striked off. This second one will get striked off because it's 5 seconds, and then for this 10 second one, this 10-second one is gonna get halved to 5 seconds because it only gets 5 seconds. So now this becomes a 5-second time. But then let's say that more jobs get allocated on the CPU, so you get another 3 seconds, get a 12 seconds, and a 20 seconds. Well, then this 5 can just slot straight in here, and it'll hold in the queue its order. So you can see again, it's going to sort it based on new jobs that are coming in and other jobs. And yeah, it keeps this order in the queue. So then obviously this will get striked off, this will get striked off, this will turn into 7 seconds, this will turn into 15. And then there'll be more jobs down here. And it just keeps on holding it like this. And I think that's all there is to it. This can sort of help slightly solve the starving issue by like bigger jobs slowly get whittled down into smaller and smaller ones. But I think that's all we need to know for shortest remaining time even.
Okay. Notes. Okay. Red. There. So when you have shortest job first and shortest remaining time first, they are sorting based on estimated burst time, how long it would take on the CPU. We can generalize this away from burst time to get priority scheduling, where basically every single process is given a priority rating. For example, Windows has 1 to 31. Every process has some priority between 1 and 31. And I believe the closest to 31, the higher the priority. So the higher priority is better. They're the ones that get more time on the CPU. And basically, it works in that it works the same concepts as the other two, the previous two. But now we can say this is important. We can control priority in a more refined way. We can put more variables in to define what a priority is, and we can artificially say this one here, this is important. Do it now. This is a 31. We have to do it now. Ignore everything else until it's done. And that's usually called boosting. You can boost priority for a little while. For example, when you're focused on a window, that will often boost the priority, so it will quickly get a lot of CPU time, be able to react very quickly and catch up on anything it might have missed. And then over time, so every single cycle, it will lose a bit of priority until it goes back to where it should have been normally. The good side about this is that it prevents, or it means that important jobs are done quickly. So if it's important, you want it done quickly, so it will be done quickly. Downside is that it can lead to starvation. If you have a fair few, or a consistent source of high priority jobs, then low priority jobs won't be done. So you can starve low priority. And this can actually be mitigated slightly by using a thing called aging, where basically the priority of a process will increase as it ages. And by doing that, you'll make sure that nothing will get too starved. Eventually, it'll be seen to, because eventually it'll reach higher than all the others. Though by doing that, then potentially you're going to end up screwing yourself. Otherwise, if you have particularly cyclical sources of processes, because then you might get a bunch of high priority processes aging up, and then overwriting things that need to be done quickly. So swings and roundabouts. Sometimes it's good, sometimes it's bad. Generally speaking, though, it is a generalized version of these two that lets us give a bit more fidelity in what we're picking. The final type we're looking at is called round robin. This color, I think it's that color. Yes. Okay, so round robin is preemptive first come first serve. You say it's still using a queue, but now it is a circular queue. So rather than it being sort of, here's a thing, here's a thing, here's a thing, we do this, then this, then this, circular queues let you cycle around them. Or to look at it as a regular queue, what you're basically doing is you do something, and then as you hit your time limit, because it's preemptive now, we're doing time sharing, you have a specific set amount of time. When you hit that, it's already been removed from the queue. When you did it, you put it back on the end. And then this one gets done, it gets put back on the end. So you do this. And by doing that, you are getting the benefits of first come first serve, and that you have a fair distribution. Because combined with a time limit, then you're making sure that everything will have a fairly fair distribution. But you're also making sure that you can use this in a general purpose operating system. And as a point, the name for like the time slice something can have is called a time quantum. Quantum meaning unit. There is another version of round robin, which is called priority round robin, which takes in, it combines first come first serve with priority scheduling, basically. It's one of the more common ones in actual operating systems. It means that you are keeping that queue, but you're also sorting the queue, and also making sure that things that have just been done aren't done again unless they're really high priority. I think that's it. Let me double check my notes. Yeah, that's it. Short one today. Basically just going over sorting and stuff. Not sorting, scheduling and stuff.
Mm-hmm.
Anything else I can read down? No, I think that's everything. Tomorrow is... What's tomorrow? Bundle E. Oh, I think that's files. Or something like that.
Tomorrow, it's handling, I think, file management, yeah?
Yeah, files.
I think it's 2 actually. It might be memory as well.
Yeah, I think files and paging, segmentation.
And I/O scheduling.
Yes. Not as huge as yesterday, but not as small as today.
No, it's quite nice, that topic.